Hey, welcome back everybody. Example 12.5, we're looking at gravity and as it pertains to the distance above or below the surface of a planet. That is the radius that we are away from that planet's point mass. So example 12.5 says you are talking to friends and they say that, well, when you get up to a certain height above the Earth, gravity is just a lot weaker. And what you're going to point out to them is that's not true. Gravity is still very strong. Really, the reason astronauts seem to have no weight is because they're orbiting the Earth. If they stopped orbiting, gravity would pull them down very, very quickly. So that's at least the point here, but we're going to prove it to them by convincing them or by calculating how much the gravity actually is at 300 kilometers above the Earth's surface. Okay, so we're 300 kilometers above the Earth's surface. So let's just say here's the Earth, okay, and here's our space shuttle, okay, orbiting above the Earth. Usually it orbits upside down, but you know, whatever. And that is 300 kilometers. Again, we're going to have to convert that to meters. But that's our height. Our height is 300 kilometers. Don't forget that we need to know how far we are away from Earth's point mass, or the point where all gravity acts towards. And that's our radius of the Earth, r. So in order to get our working radius, we have to add the height to r. Well, our height is 300 kilometers, and we need to convert that to meters. A kilometer is 1,000 meters, so we could probably do that in our heads. That would be 300,000 meters that our space shuttle is up above the Earth's surface. And we know the radius r because it's in our calculators. Okay, so we want to find how much gravity there actually is, how much acceleration of gravity there is. Well, we have an equation for that, which we derived just in the last section. The acceleration of gravity, g. Now, it's not g at the Earth's surface, it's going to be g at this height above the Earth's surface. That's going to be capital G, the gravitational constant, times the mass of the Earth, divided by lowercase r squared, which really, that's going to be g times the mass of the Earth, which I think, by the way, I had us key this into our calculator as simply E. I think if you put in m, I think we put that as the mass of the moon, but anyway, that's the mass of the Earth divided by, in this case, we'd have to add our radius of the Earth plus 300,000 and then square that, because this is from here up to here. Sorry about the crooked arrow. That is really our working radius r. We're adding the radius of the Earth to the height we are above the Earth. Okay, well, and the reason I'm not writing these numbers out is because we should have these keyed in our calculator. So let's take g times mass of the Earth, I think we put that in as E, and divide that by the quantity r plus 300,000, and then square it. And that should give us the gravity that there is at that height above the Earth. So we do know as you increase your altitude from the Earth's surface, gravity decreases. And your friends think, well, it's a lot less up there. That's why they're floating. Well, what do you get? You multiply this out. I get the gravity, the acceleration of gravity up there at that height is 8.93 meters per second squared. Well, gravity at the Earth's surface is 9.81 meters per second squared. This is 8.93. This is still very significant. There is still absolutely gravity up here at this height. the fact that the space shuttle is orbiting so fast around the Earth is the only reason it's staying in orbit, and our astronauts feel weightless. But this right here is proof that there's still significant gravity even at 300 kilometers above Earth's surface. Okay, there we go. That's example 12.5. I'll look for you on the next video on example 12.6.